Okay, hi everyone. So I'm Christopher Manning. I'm a faculty member at Stanford University. And so what I thought I'd tell you about today is about deep learning, which is this exciting new approach to machine learning that's become very successful over the last few years, and how that can be applied to language understanding, which is the main field that I work on. But in doing this, I actually hoped I could achieve another goal, which was I hope I can sort of give you a sense for the kind of math that you learn, if you're lucky, at the end of high school, things like linear algebra and calculus, that really they're right at the heart of what goes on in these deep learning systems. In some sense, they're sort of no more complicated than that. Okay, so the general idea of machine learning is for the kind of stuff that you're doing, like in these programming competitions, that you're programming computers to precisely follow your instructions and compute something. And when we're trying to do machine learning, we're trying to do something more than that, that we're trying to program a computer so it can learn things on its own. But for the bulk of what's been done inside the machine learning world, the way that that happens is nevertheless most of the design work is done by human beings. So humans design representations and features that will be useful to learn different kinds of things. I mean, so my little example there on the right is for a natural language system that finds the names of people or organizations and things like that, and some human being has very carefully hand-designed features that will be good at matching patterns for person names. And so if you're in that world of machine learning, to a fair extent, the machine's not actually learning very much. That a lot of the cleverness has come from the human being, and the machine learning is mainly actually sort of fiddling around weights. It's sort of a kind of a numerical parameter optimization. So in contrast to that, the idea of representation learning is to say that, well, maybe we could actually expand the amount that our computers learn, and we could get them to learn useful features and useful representations that will allow them to understand and solve problems, just like that's what human beings do. If you have a new problem, you're trying to work out, well, what kind of representation and things about it will let me solve what's going on. And so within the area of representation learning, the exciting approach where there's been a lot of work lately is this idea of deep learning. And the idea of deep learning is essentially, it's a neural network system where there are multiple levels of representation, and the hope is that inside those multiple levels we can start to learn useful features and representations for different problems, starting from right down the bottom where we have just a fairly raw input, which might be sounds or images or words. And so the core of what we have is a so-called neural network, where these are loosely inspired by human brains, but are very much an artificial neural network. So the idea of these artificial neural networks is they can represent concepts as vectors of real numbers. So concepts are sort of distributed over a pattern of numbers. And then what we're going to do is kind of compute different representations by having different layers in the neural network. And this tangle of black lines is inspired by the idea of connections between neurons. But when we actually implement it in our neural network, what this tangle of black lines actually does is turns into a matrix. And so what we're doing is taking a vector and multiplying it by a matrix, maybe adding on a bias and getting the next layer and going on like that. Okay, so that's a teeny bit about deep learning. I'll get back to that in just a minute, but let me also then tell you a little bit about what is computational linguistics or natural language processing. So computational linguistics is at the intersection between artificial intelligence style computer science and then doing things with linguistics, which is the science of human languages. So the general goal is how can we process, so to speak, or understand what's happening in human language materials so that computers can interact with human beings in the same lovely way that all of our science fiction robots tend to. And so that's everything from agents that can, understand making appointments or ordering things, question answering systems, machine translation systems, all these kinds of things. So any of the things that you see around you now, things like Siri or Google Assistant, Cortana, are all examples of natural language understanding systems. In general, the development of mobile and cell phones has been a huge drive for the development of natural language processing systems, precisely because once you have these small mobile devices, it's really convenient if you can use human language as an interface modality. Okay, so in the commercial world, these days, computational linguistics is everywhere in the commercial world. Some things are actually pretty low level. So, you know, the green wiggly underline in Microsoft Word is contextual spelling correction. So there is a correctly spelt word, but, you know, in this sentence there are many approaches. It's the wrong spelling of there, as you hopefully learned in some English class. And so that's a little bit of computational linguistics to understand enough of the sentence context that it can get that right. When Google's trying to find the right advertisements to show to you, that's also doing a kind of a semantic matching between words, so it knows the resort's kind of like a ski lodging. So that, you know, is fairly low level as well, but makes billions of dollars a year. And then that goes on to the sort of more high level things, so something like Amazon Alexa. Okay, so what happens when we bring these two things together? So actually the first place where deep learning really proved itself super successful was in building speech recognition systems. And so starting in 2010, some students of Jeff Hinton working at Microsoft showed that you could sort of replace the conventional kind of signal analysis that people had worked out for speech recognition systems with deep learning approaches to doing analysis of people's voice sounds to do speech recognition, and it almost immediately produced huge improvements in speech recognition accuracy, about 1/3 error reduction. So these days, for your cell phones, that they actually do an amazingly good job at recognizing the words that you say. And that's largely been because deep learning has been pushed out into being used for speech recognition on all the kinds of cell phones that you can buy. And so the state of now is that actually taking sounds and turning into words, not quite flawless, but, you know, nearly always works. And the part that doesn't work is that the cell phone then doesn't know what you're saying. It can't actually understand the language being used, even though it's recognized the words. And that's the main thing that I want to talk a bit more about later today. The most dramatic breakthrough result of deep learning was then in computer vision, of building deep learning systems for doing object recognition, so recognizing a Persian cat and a Siamese cat and a quail and all of these things. Vision is a good example for getting a sense of this representation learning, of how you get more abstract levels of representation as you learn in a deep neural network. So on the first layer, you get edge detectors, and you get some texture units, and you kind of get color blotch patterns, similar kind of things to human or animal visual systems have in their earliest layers of neural processing. But then when you get up into the higher levels, so in the higher levels, you'll start be getting things that'll be recognizing circular shapes and more complex patterns and things like that. And then once you go up to the third level, you tend to get more part detectors, that you'll get things that'll be recognizing eyes or ears and things like that. Okay, but what I want to do for the rest of this time is actually turn this into a technical talk and tell you something about how we can start to learn these distributed representations. And so we're not going to do full natural language understanding here. What I'm hoping to start to show you is how we can build these things called word vectors, which are very useful. And so the starting off contrast here is, what have people generally done with human language in some kind of natural language processing or web search system? And so the general result is that just words have been regarded as words. We have words like hotel, conference, competition, whatever they are. But if you think in machine learning terms, a symbol, a word, is kind of like a huge vector that's zero almost everywhere apart from one position, because this is sort of the vector that says the word isn't competition, the word isn't hotel, the word isn't house, the word isn't this, the word isn't this. Eventually, the word is conference, which a deep learning person calls a one-hot representation. Well, why are these kind of representations problematic? Think of an example like web search. So if a user searches for Dell notebook battery size, we'd like to have our web search engine match and return pages that maybe talk about Dell laptop battery capacity, even though the words differ, notebook versus laptop, size versus capacity, or Seattle motel, Seattle hotel. So you want to match words that are semantically similar, even though they're different words. And if we're working at the level of symbols with our one-hot vectors, there's kind of no natural way to do this. So if you look at these two vectors, and if you take the dot product between the vectors, that there's a dot product of 0. There's no natural similarity, that these are actually orthogonal vectors. There's no sort of straightforward way to tell the similarity between different symbols. And so what we want to do is come up with a better solution than that. And so here's an idea of how to do that. The idea is, well, if we want to learn about a word banking, maybe what we could do is get a whole lot of text, and then we'll find a whole bunch of context in the word banking we'll use. And so we'll get some idea of the meaning of the word banking by just looking at what words that are out here. So there'll be debt and regulation, hodgepodge, government, various things. Maybe we'll start seeing words about deposits and so on. And you know, you could think of simple things that we could do of just sort of counting up how often different words occur. And they'll give sort of some idea of how the word banking relates to other words. And that's referred to as distributional similarity-based learning of word meaning. And so for deep learning representations of words, we do a version of that. So what we're going to do is this time we're going to say, well, we're going to represent each word by a real valued vector, so a kind of a sequence of real numbers. And what we're going to want to do is learn representations as a vector so that just naturally a word is going to show its similarity relationships to other words. So we can take these vectors and put them in a vector space, and we're just going to want to have numbers in these vectors, so words that are similar in meaning are then going to be similar to the space. Now, even this vector is an 8-dimensional vector, and it's very hard to draw an 8-dimensional vector space, so I'm doing a 2D projection. But in reality, we're not even going to want to work with 8-dimensional vectors. Commonly, we end up working with hundreds of dimensional vectors. So how do we go about doing that? Okay, so, well, we're going to have a word that is our center word, what banking was, and we're going to try and predict words in the context of banking. And so at the top level, we're going to say our goal is to predict words in the context of banking, given banking, and we're hoping that we can give a high probability to the words that actually occur. And so our loss, the extent to which we're doing a bad job, is the extent to which we don't predict the right words. If we could always predict the word with probability 1, there'd be no loss, but in reality, we lose. So then what we're going to want to do is have a probability model to predict the words that occur in the context of the other words. And so, right, so we've got the center word, the surrounding context words, and we're going to have this probability distribution of another word occurring in the context of a word. Well, what kind of probability distribution could we use? And the idea we're going to have is, so for each word, so the center word and the context word, we're going to have a vector that represents each of those words. And we're going to define the probability distribution directly in terms of those vectors. So if I just sort of break apart a little bit what this is doing. So in the top part of it, we were doing this dot product. And so the dot product means that you take the sort of paired components of the two vectors, you multiply them together, and you sum them. So a dot product is a sort of a similarity measure, because if you have positive numbers in corresponding positions, you get positives coming out, or negatives in both positions, you get negatives coming out. Whereas if you have opposite sign, you have sort of negative coming out. So it's sort of a positive to negative similarity scale. And if you have the big components in the same places, that also means that your dot product gets larger. Okay, so here we've got this dot product. And then what we're going to do is be then considering all the other words that could have occurred in the context. So we're thinking about all the other words in the language and also looking at what their dot product is. And so then for the rest of the equation, we're then embedding this in what's referred to as a softmax. And a softmax is a way of turning things into a probability distribution. So in some sense, it's pretty easy. So in the numerator, we're taking our dot product and we're taking e to that dot product. So the dot product can be positive or negative, but if we exponentiate it, it always comes out non-negative. And so that's good for getting a probability. And then if you have a bunch of non-negative numbers and you want to turn them into a probability distribution, there's this super simple way to do it, which is that you just sum all those numbers and divide through by them, and then you have to have a probability come out that that's the normalization. So that gives us our probability function. So given that probability function, what we want to do is say, okay, well, we have this model for predicting words which has a ton of parameters. So we get all of these parameters. So we have a big long vector of parameters where each word is being represented by a vector, has a center word and an outside word. And so we're just getting a vector for each word, and we concatenate all those word vectors together, and we get a really long vector which might have millions of parameters on it. And then we say, okay, machine learning system, we want you to change all of these real numbers so that our probability model maximizes predicting the probability of outside words. So how do we do that? So we do that by the idea of gradient descent. And here's the simple model of gradient descent. So here's a simple little function. It's just x squared plus 2y squared, where we've got x and y. And we want to find the minimum of this function. Well, if you've done some calculus, you'll say, well, that's easy. I can differentiate that and find the minimum of this function. But if you're not so smart, what you can do is you can just pick some, well, we actually are still going to use calculus, but you can pick some random spot and say, okay, let me see if I can work out the slope at this point. And so the slope at this point is the derivative. And if I can work out the slope at this point, I can just walk a bit of distance in the direction of the steepest slope. And then I can say, well, let's work out the slope again at this position and walk a bit of a distance in that direction. And if I just keep on repeating that over and over again, I'll sort of walk down to the minimum. And that's the idea of gradient descent. And by and large, deep learning models, because they're sort of much more complex functions that it's almost impossible to do something with analytically, that people are learning good settings by gradient descent. Right, so this gradient descent, just one more time, right? So here's a single variable function, x to the fourth minus 3x cubed plus 2, which hopefully a lot of you can work out the derivatives of. But what we're saying is if we're at a particular point, the gradient there, the slope is positive. And so if we subtract off a little bit of the slope, we'll be moving towards the minimum. So we have positive slope, we subtract a small positive number, and that's moving us down the function towards its minimum. And so that's the general recipe of gradient descent. We just have some value for our parameters, which we initialize randomly. We work out the slope at the position of our current parameters. We move a little bit in the negative of that direction, which moves us downhill, and we just repeat this over 1 billion times on our very fast computer, and we're done. And so to be able to take models like my word vector model and work out, gee, what is the slope in this whole model? I mean, really what we're doing is no more complex than applying the chain rule a lot. And so if you've made it through doing differentiation, this is sort of all that's going on. So the idea is if we have y as a function of u and u as a function of x, then we can have the chain rule where we can work out the rate of change of y with respect to u times the rate of change of u with respect to x, and this will work out our slopes. And so that's essentially all we're going to use. It's a little bit more complicated for our example. I'm not going to go through all of this math right now because my time will run out on me. But we start with our loss function, which we take the log of because that makes it easier. We start with our probability distribution, and then we want to take the derivatives of our probability distribution with respect to our word vector parameters. The thing that's a bit complex that a lot of you won't actually have seen is this is now multivariate calculus, so it's having to take the derivative with respect to each element of the vector. And so that's a sort of a log of a quotient, so we can turn that into log A minus log B and take the derivatives each side separately. The numerator is really simple. We go on to the denominator. This is where it gets more complicated because we have functions of functions. So we use the chain rule here, and we use the chain rule down here again to make progress through it. But it's really no more complicated than using calculus, using the chain rule. This is also something that it's great to understand, but one of the things that's happened in modern deep learning is you don't actually have to be able to do this anymore. So that for the recent great software frameworks such as Google's TensorFlow, one of the joys of TensorFlow is providing you write down the function, it'll work out the calculus for you, and you don't even have to do it for yourself. Okay. But the really interesting thing is that what you can do is that you can start with just random vectors for words and say, start here and run gradient descent. And by sort of repeating over and over again that simple idea of just sort of walking downhill, sort of almost a miracle occurs that the words, vector representations will just shuffle around in the vector space. And so when it'll come out, that they will just come out so that words with similar meanings end up close to each other in the space. And so that's a very useful thing for sort of solving these problems that we were talking about. So here's a little example. So in this model, if I say, what are the closest words to frog? The closest word is frogs. That's a good sign. The second closest is toad. It gets a little bit harder to know what's happening after that, but luckily Wikipedia to the rescue. So a Latoria is this beautiful green tree frog, and a Leptodactylidae is this not quite so beautiful frog over there. This is a rana. Lizard, not perfect. I guess we would have been better off with a salamander, but it's somewhere in the same space, and that's another kind of frog. So it's just sort of naturally learned a good meaning similarity between words. And these kind of meaning similarities have then been sort of really, really useful. A couple of years ago, Google started using these methods in their web search, and they built out a model which they called RankBrain. But it's a word vector representation of words, just like I showed you. And so the whole idea of it is that if someone is searching for car parts for sale, that these word vectors are good enough that you can do a match with different words for something like a document that says it's selling rebuilt transmissions. And so these kind of word vectors aren't actually necessarily useful when you're searching for really, really common things. Like if you're searching for Taylor Swift, you can just match the words Taylor Swift, and it's not going to help you using these kind of word vectors. But as soon as you're trying to do the harder matching of queries, then they're super duper useful. And indeed, Google reports that this kind of word vector ranking is actually the third most important signal that they now use in their web search. From here, people go on to much, much more complex deep learning models. So here's a model that was built by Professor Fei-Fei Li and some of her students. I think she's actually going to be talking at Harker in about a month in the science fair. And so this is sort of a much more complex model that starts with images, does a deep learning image analysis system, then decides on subparts of the image to focus on, and then is going to generate some text from those pieces of the image. But in practice, to train these models, we're doing exactly the same thing. We're having a loss function at the right-hand end, and we're doing calculus, the chain rule, to work out derivatives going backwards so we can do gradient descent updating of parameters. And so this is the kind of output it produces. So it finds areas of interest inside an image and then gets out text to describe them. Ball is white, ground is brown, elephant is standing, and things like that. Okay, so I haven't been able to obviously teach you everything there is to know about deep learning, but I hope I've given you at least some sense that understanding language, well, that still remains a challenge that's far from solved, and so it's a sort of a great, exciting area. But on the other hand, these kind of deep learning approaches are clearly allowing us to have a way of sort of having human-like abilities to understand images and understand language, which is well beyond what we could do 5 years ago. And then maybe some of you I snowed slightly with technical details, but I mean, the other thing I wanted to sort of give a little bit of a sense of is sort of this artificial intelligence or deep learning, that it's not voodoo and magic, that when it comes down to it, at the heart of it, that 90% of it is linear algebra and applying the chain rule, which is actually kind of stuff that quite a few of you have seen, or else you'll be seeing very shortly in your schooling. And so there we go. Thank you.